Let's look at a little bit more involved problem of finding the magnetic field through a current carrying wire. And notice that for sections 1 and 3, if we take a little segment ds for each one of these segments, that we will find out that the current is in the same direction as the current and ds are in the same direction, because if we look at this point here, C, they both point to it in the same, without any movement. Yeah. So there's ds, which is actually should be the distance from C to I, would be parallel, which means that for segments 1 and 3, theta is 0 degrees, or you can even think about it, 180 if you want. That's also fine, because it's along the same line from point C to that segment. There's no deviation. That implies that B at segment 1 equals 0, which also equals B at segment 3. So now the only thing left is B2, and at B2, because now the line coming from C to that segment is coming on to a circumference of a circle, then theta is by definition pi halves, right? If you go from the center to the circumference of a circle, it's always going to be perpendicular. That's by definition of what a radius is. So now we have that dB2 is going to equal mu naught over 4 pi times I ds sine of pi over 2 radians divided by, now the distance from point C to anywhere on this arc is going to be r squared, right? Which means that B2, the integral of all this, if we integrate ds, we're just going to get the arc length, which is r theta. So we get mu naught I times pi over 2 times r. This is what S would be if we integrated all of this. Sine of pi over 2 is 1 all over 4 pi r squared. Note here that the integral of ds in this case would be the angle pi over 2 radians times r. This is the arc length of segment 2. So if we simplify this a little more, one of the r's cancels, the pi will cancel, and the 2 multiplied by the 4 will give us mu naught I over 8r. And because there's no more segments, then then B total would equal B1 plus B2 plus B3, which equals mu naught I over 8R, the only contribution.